Hi to all. I am A.V. Laxman Rao, Assistant Professor in Physics, Department of H&S. In today's session, I am going to explain you about one important approximated model called as konig-penny model. Let us discuss about what is this konig-penny model and what is the use with this konig-penny model. My session have been divided into two important parts as first, I am going to explain about the model called as konig-penny model, the approximated model, and the second one is how we can understand the konig-penny model by plotting a graph. That is nothing but by plotting a graph, the advantage is we can explain the formation of allowed energy bands and forbidden energy gaps. That I am going to explain at last. First, let me take what is this model, konig-penny model. Now, König and Penny, these two are two names of two scientists. Actually, these two scientists were approximated a model about the potential energy, variation of potential energy of a moving electron in a periodic field. Already there was one theorem which was already proposed before this König-Penny model. The theory is called here Bloch theorem we are calling. According to Bloch theorem, we know that when electron is moving in a periodic field, here I am taking a crystalline solid as a metal. Now let us assume that there is one electron here and it is moving from one end to another end as like this. Then according to Bloch theorem, we know that the potential energy is varying as in this form. In this we can see that here slow increment attaining the maximum value of the potential energy and slowly decreasing the potential energy can be seen as the electron is moving from one positive ion site to another positive ion site with respect to distance as like this, and if you take on y-axis as the potential energy according to Bloch theorem is varying as like this. But unlike this form, according to this König-Penny model, how that potential energy is varying when electron is moving in a periodic field, now we are going to see. It is nothing but the revised theory about the variation of potential energy of an electron which is moving in a periodic field. Now, let me move to the actual König-Penny model. It was approximated by König and Penny. It is an approximated model, and this model consists of square wells and as well as rectangular, square or rectangular that wells can be taken. It is made up of simpler potential in the form of an array of a series of square wells can be seen in this model. Let us see. Here I have taken one crystal in which atoms or ions are arranged in a systematic manner, and this dot let me take as a negatively charged electron. By applying electric field in one direction, external electric field, this electron is experiencing force. Then how the potential energy is varying of this electron with respect to its position, that was explained by this theory. Now according to this model, when electron is moving from one end to another end as like this, let us assume that this electron initially it is at far away from the positive ion site. Then obviously we can say that the potential energy can be expected as maximum. On y-axis here I am taking the V value, and on x-axis I am taking the position of that electron in a periodic field. Now, when electron is far away from any positive ion site, in general, the potential energy is very high. It is maximum of that electron. As the electron is moving towards the positive ion site at a particular distance, when it reaches, all of a sudden, the potential energy is going to be dropped here to 0. Suddenly it is going to be dropped. Whereas in Bloch theorem we have seen that the potential energy slowly it is increasing, attaining the maximum value, and slowly it is decreasing. Whereas according to the König-Penny model, when electron is far away from the positive ion site, its potential energy is maximum, and as it is moving towards another positive ion site, slowly no change can be expected, rather a step change can be expected. Step change is nothing but here as the electron is approaching to the positive ion side, suddenly the potential energy will become zero. And this zero will remain up to some distance, and when the electron reaches the middle of two positive ion sides, then all of a sudden the potential energy will rises to maximum value, rather increasing slowly and decreasing slowly. Here all of a sudden the potential energy rises to maximum, and up to some distance the potential energy is maximum only. Still further, if electron is moving towards another positive ion site, then all of a sudden the potential energy when electron reaches to the another positive ion site, it is becoming as zero. Now if you observe this approximated model, a series of square wells can be seen here. So this model is approximated as like this. All the region 1 is nothing but where no potential energy is there. It is nothing but V equal to 0. We are calling it as a potential well. We are calling this square well is called potential well, and where the top is closed, it is nothing but the potential energy is maximum. We are calling that region 2 as potential barrier. It is nothing but according to this model, a series of potential wells and potential barriers can be expected. First region 2 you take, maximum potential energy is there. Region 1 immediately can be seen, in which the potential energy is 0. And again it is going to be repeated, region 2 and again region 1, where the potential energies are suddenly changing to 0 and suddenly it is changing to maximum. So a series of potential wells and potential barriers can be seen in this model. It is nothing but this model is well separated by potential barriers and potential wells. One potential barrier to another potential barrier, if you take, they were separated well by using the potential wells. So whatever the model was approximated as like this, we are calling it as here König-penny model we are calling. It is nothing but the variation of potential energy of a moving electron in a periodic field. With respect to its position, actually the potential energy is varying. Here that variation of potential energy is also said to be as according to the lattice constant. Here whatever the distance from one electron to one positive ion site to another positive ion site is there, that is called as A, which is nothing but lattice constant we are calling. So one positive ion site to another positive ion site, the distance is always same will be there. That distance is called lattice constant, and the potential energy is varying with respect to the lattice constant here. So if you take the potential energy of the electron as V and the position of that electron as X and the lattice constant as A, we can say that when electron is very nearer to the positive ion site, the potential energy is 0. When electron is in the middle of two positive ion sites, position is in the middle of two positive ion sites, then the potential energy is going to become as the maximum value. By taking the boundaries of the regions and how we are calling that region as, how it was named as, and the potential energy in the two different regions and width of that potential energy, width of that potential widths, how much was taken, and the regions of each that potential barrier and potential well. If you take as the parameters, we can say that there are two different types of regions are there, region 1 and 2. If you take region 1 is called as your potential well. Potential well is nothing but the region in which the potential energy is 0. And the width of the potential well here in this example was taken as, this is the potential well and its width is taken as A. Now the region for this is, it is having some restricted region as less than A and greater than 0. Which is why, that's why you see X is greater than 0 and X less than A. That region wherever you take, which is nothing but a potential well only. And the second region is called as a potential barrier approximated model as like this we can take. The second region is called potential barrier, in which the potential energy is maximum and the width of that potential barrier was taken in this approximated model as from here to here is nothing but 0 to B. 0 to minus B is nothing but direction we have taken as a negative direction, but the width value is B only. So this is called as a potential barrier and this is called as the potential well, and immediately another potential barrier and another potential well can be expected. That's why the region was taken as like this. So this model is nothing but how the potential energy of a moving particle is varying with respect to the position of that electron in a periodic field. According to konig-penny model, this model is as like this. It consists of a series of potential wells and the potential barriers. Now, by taking as like this, these two scientists were applied Schrödinger time independent wave equation to that moving electron. According to Schrödinger time independent wave equation, we know that when electron or any particle is moving particle will have the wave nature that we know. So, according to Schrödinger time independent wave equation, for a moving particle we can write an equation as like this. But the thing is, electron is moving across potential well and potential barrier. In potential well, we know that V equal to 0. Substituting potential well potential value as 0, we can get here, this is becoming 0, so we can get one equation as like this. When electron is moving across the potential barrier, the V value can be taken as V max. So V max, if you have substituted here, where we will get another equation as like this. By taking these two equations, these two scientists were approximated, these two scientists were assumed in different ways as the height of the potential barrier increases, the width of the potential barrier decreases, and also they have approximated, they have assumed in different ways, and finally they have concluded the equation as like this. The potential energy of that moving electron, how it is varying, means according to these two scientists, they have derived one expression called as like this. So according to this konig-penny model, the final equation they have derived. Here we are not going to derive that equation. We are writing the final equation as P sin alpha A by alpha A plus cos alpha A equal to cos Ka. I am writing the final equation of this konig-penny model as like this. Now the thing is, what is the meaning of this equation? They have derived this equation, but is it telling us about any important concept? Means yes. The formation of allowed energy bands and the forbidden energy gaps of an electron can be explained by using this equation. Let us see how we can understand about this equation. Now, according to these two scientists, the equation I am writing here as P sin alpha A by alpha A plus cos alpha A is equal to cos Ka. Now, we know that this is nothing but the LHS part. This is nothing but LHS part, and cos Ka is nothing but RHS part. LHS and is equal to RHS. As like this, first you take. Now, what is the parameter that was given in this P is there? What is the meaning of P? According to these two scientists, the P value was calculated as like this, and this P is called as the scattering power of that electron. So, scattering power is taken as a P, and the P value is measured or calculated as like this by these two scientists. Scattering power of the potential barrier P have been written as like this. Now, what is V naught into B in this equation? V naught into B. V naught is nothing but V max. As like this, if you take V max into B. V max is the height of the potential barrier and B is the width of the potential barrier. Height into width. Height into width will give the barrier strength. And very important parameter in this equation is alpha. What is P? We know. Sin and cos alpha, we know that sin and cos are the periodic functions, but there is one important parameter is there in LHS term, that is alpha. Alpha they have calculated as alpha is equal to 2 pi by h into under square root of 2m E as like that. Alpha is equal to 2 pi. 2 pi is constant value only. H is nothing but the Planck's constant, that also we know. Under square root of 2 is here also constant only. And M is the mass of that electron, but E is the energy of that electron. It is nothing but alpha is directly proportional to E. It is nothing but there is some relation between alpha and E. So what is that relation? It is nothing but if you do square of that equation, alpha equal to 2 pi by h into under square root of 2me, alpha square can be written as like this, and overall here the value of that alpha square equal to 8 pi square into me by h square, whereas the E value, energy of that electron, moving electron, can be written as alpha square h square by 2 pi square m as like this we can write. Now if you take the RHS term, RHS term consists of a periodic function cos, and A is nothing but the lattice constant of that crystalline solid, and K is nothing but we are calling it as wave number we are calling. So K value they have calculated it as plus or minus n pi by A. N values can be taken as n equal to 0, 1, 2, 3 as like this we can take the values. So overall all the parameter values they have taken here as like this. So by taking as n values 0, 1, 2, 3 and pi is the constant value, A is also constant, it is nothing but K values depended on n values. As the n values will vary, K wave number values will also vary. And very important thing is alpha if varies, then the energy values will also vary of that moving electron. Now we know all the parameters whatever are there in this equation, that is P sin alpha A by alpha A plus cos alpha equal to cos Ka. Now how we can understand about that equation, how it is telling us about the formation of energy bands and the formation of forbidden energy gaps by using this equation. To understand about that, first we take here we will take the RHS term. RHS term is here cos Ka. We know that K value is nothing but plus or minus n pi by A. If you have substituted that K value here, cos plus or minus n pi by A into A get cancelled. We are getting cos n pi, where n values are taken as 0, 1, 2, 3 as like that. So cos n pi, for any value of n, cos n pi values can be taken as minus 1 to the power n, where n values can be taken here 0 or 1 or 2 or 3, any value can be taken. So minus 1 to the power 0, minus 1 to the power 1, minus 1 to the power 2, like this if you go on write any value of n, the minimum and maximum value of this cos n pi is plus 1 to minus 1, in between no values can be taken. So plus 1 is the here 1 value and the minus 1 is the lower value can be taken as like. So if the limit are here plus 1 or the minus 1 can be taken. So here RHS term is having two limits, that is plus 1 and minus 1 as the two limits. Now if RHS is equal to LHS, whatever the limits of the RHS values are there, they should also be applicable to the LHS term, where LHS in which periodic function sine or cos is there. That's why let me plot a graph of this periodic function and let me represent these limits in that periodic function by taking on x-axis the energy of that moving electron. Here I am taking this as the line on which I am taking the alpha A values as x-axis, and on y-axis this let me take as y-axis on which I am taking the entire LHS term as like this, which is function of the energy. Now periodic function is cos or sine is there. Let me draw a periodic function as like this, a periodic function. Now here the limits of this RHS applicable to the LHS also. That's why let me take dashed lines here as the limits which are intercepting the periodic function as like this. Now wherever the periodic function and the dashed lines were intercepted, that plus and 1 and minus 1 are there. From there you draw a straight line, perpendicular line on the x-axis where alpha values are there. Then you came to know here what are all the limits of this energy of that moving electron. Now, if I draw a perpendicular line as like this, and as well as from here to here as like this, whatever the region was formed here, they were called as here allowed energy bands we are calling. Here also in this side also, here we can take that as the allowed energy band. Now, between one allowed energy band to another allowed energy band, there is some gap is there. That gap is called as the forbidden energy gap of that electron. Here, the meaning of allowed energy band is nothing but where electron can exist with that energy value, and forbidden energy gap is nothing but where electron cannot occupy that region. It is nothing but it is forbidden value. It is nothing but electron cannot have that value. Either electron will have the first forbidden value and the second one as like this and the third one as like this, where electron can able to exist, and in between whatever the energy bands gaps are there where electron cannot exist, which we are calling as forbidden energy gap as like that we are calling. So overall here what is happening here is by taking this equation and by taking the RHS term of this equation, finding the limits of that RHS term and applying that limits to the LHS term, and by plotting a graph as like this, here we can say that allowed energy bands are formed and forbidden energy bands are also formed for a moving electron in a periodic field. So this is the second importance of this model. It is explaining clearly the formation of allowed energy bands and the forbidden energy gaps. So overall, if you have plotted a graph as like this by taking alpha values on x-axis and on y-axis the entire LHS value, where alpha is there which is related to the energies, we can get here the thick vertical lines, vertical boxes as like this, which are calling as which we are calling here as allowed energy bands. This side also allowed energy bands, all this, and whatever the gaps are there, which we are calling here as forbidden energy gaps we are calling. Now, based on this profile, based on this form of this graph, we can say that as the alpha A values are increasing, the width of the band will also increases. It is nothing but you see here, if you take as the width W, here you can say here as the width of that potential barrier was increased here. So this band to this band, when you compare, width is increased. This band to this band, if you take, the width is still further increasing. As the alpha values are increasing, here the width of the allowed energy bands are also increasing, as like that we can say. So this is the second importance of König-penny model. The first one is how the potential energy is varying when electron is moving in a periodic field. That approximated model and the equation we have seen. And the second one is this one, in which allowed energy bands and the forbidden energy gaps, how they were formed by using the König-penny equation, can be explained as like this. So the conclusions of this topic can be said as, if you take a König-penny model in which square or rectangular form of boxes can be taken, and these square or rectangular form of boxes are called potential wells and potential barriers, and they were arranged in series. An array is nothing but in series they were arranged. If first one is the potential barrier, the next immediate region is potential well. Next region can be expected as potential barrier. That form can be expected as either in the square or rectangular form, approximated model. And the second one is the variation of potential energy of a moving electron is dependent on its position, electron position, where it is located. If it is located exactly at the center of the positive ion side, potential energy can be taken as 0. If it is located far away from that positive ion side, then the potential energy is maximum. It is nothing but potential of that electron is varying with the periodicity of that lattice. And the third one is Vmax can be expected in the middle of the two successive positive ions, and the V can be expected as 0 when electron is at a positive ion site. Next one is by taking the konig-penny model, we can successfully explain about the formation of allowed energy bands and as well as the forbidden energy gaps. Here energy gaps are nothing but forbidden energy gaps are nothing but whatever the gaps are there between one allowed energy band to the next immediate successive allowed energy band. We are calling them as forbidden energy gaps. So all these concepts can be successfully explained by using a konig-penny model, which is also called as KP model we are calling in quantum physics. Thank you.